If you try to accelerate an object to the speed of light, you run into a hard physical boundary in our universe. This is Albert Einstein's math formula. As the velocity variable v gets closer and closer to the speed of light c, the object's mass approaches infinity. That physical boundary mirrors the mathematical boundaries we study in calculus. While exploring the limits of the universe is fascinating, we can apply that same logic to a more immediate challenge: mastering the algebraic evaluation of mathematical limits. Navigating these algebraic boundaries is the key to solving the most common rational function questions on your Chapter 2 exam. The foundation of all limit evaluation is direct substitution, a strategy supported by the fundamental limit laws. This is a typical rational function limit. When you see a problem like this, your first step is to test the denominator. By plugging our target value of 2 into the denominator, we get 2 cubed plus 4, which equals 12. Because 12 is a real non-zero number, we can proceed. Now we substitute that same 2 into the numerator. 2 times 2 squared minus 3 times 2 plus 1 simplifies to 3. Our final answer is 3/12, or 1/4. If direct substitution yields a real number, the problem is solved. No further work is needed. Substitution doesn't always yield a clean number. In this limit, as x approaches 4, plugging in 4 results in 16 minus 16 over 4 minus 4, or 0 over 0. A result of 0 over 0 does not mean the answer is 0, and it does not mean the limit does not exist. 0 over 0 is an indeterminate form, meaning there is more algebra to be done. By factoring the numerator into x minus 4 times x plus 4, we cancel the matching terms, leaving just x plus 4. The indeterminate form is a signal to look for those hidden factors and use algebra to reveal the true limit. At first glance, this expression appears to have no common factors because the terms in the numerator are reversed. We can bridge that gap by extracting a -1 from the numerator. This flips the signs, resulting in negative parentheses x minus 1. Now the terms match, and we can cancel them. As you write out these steps, maintain your formatting. The limit notation must appear on every single line of your work until you perform that final substitution. Accurate math won't protect your score if your notation is inconsistent. Precise labeling is essential for a complete proof. Let's test this strategy. This equation shows a limit as h approaches 0. Substitution results in 0 over 0. Pause the video now and attempt to solve this using algebra. Since we cannot factor the numerator directly, we expand the binomial. 1 plus h squared becomes 1 plus 2h plus h squared. The positive and negative ones subtract to 0. We then factor an h out of the remaining terms, cancel it with the h in the denominator, and plug in 0. The limit is 2. Expanding expressions is a reliable way to break out of the 0 over 0 trap when factoring isn't an option. In this final example, a limit with a leading coefficient quadratic. Substituting 1/2 yields an indeterminate form. So we factor the numerator into 2x minus 1 times x plus 2. We cancel the matching denominator factor and substitute 1/2 to get 2.5. Complex polynomials don't change the underlying requirement: factor, cancel, and substitute. This flowchart provides a clear path forward. Start with direct substitution. If you hit an indeterminate form, use algebra to cancel common factors, and always carry the limit notation through every step of your work. With this algebraic toolkit, you are ready to tackle these rational function problems on your exam.